Hello everyone. I'm Stephen Haben. I'm a senior AI consultant at the Energy Systems Catapult, and thanks for joining us on the Value in Energy Data seminar. The aims of these talks is to sort of show how data and digital is being applied across the energy sector, and we've got an excellent speaker today from Leo Alder, co-founder and CSO of AIM Group. I'll give a quick introduction to Leo, and then he'll give his presentation. So he's the co-founder and CSO of AIM Group, an AI platform that turns existing sensor data into early warnings of structural and mechanical change across transport and the energy infrastructure. Leo had previously worked in the structural monitoring industry before AIM and now runs the company's strategy, working directly with asset owners to help them get the most from their data. So his focus is on translating what that data shows and making sure that turns into fast, insightful, practical decisions for the asset owners. So it's very interesting today. It's the first talk I think we've had in this area, in this long series actually, so it should be very interesting. It's a great example of showing what existing data can do, but I think it also shows some real value that can be created in multiple sectors. So I'm very pleased to introduce Leo, who's going to talk on unlocking the hidden value in asset data. So Leo, if you want to share your slides, please begin.
Brilliant. Thank you, Stephen. I'll just share my screen. Just let me know if that's coming through.
Yeah, I can see that. Thanks.
Lovely stuff. Excellent. Well, in that case, oh, sorry, I've just pulled it onto the wrong screen. Is that back to normal?
I see the slides now. Yep. Perfect.
Lovely stuff. But yes, in short, we are AIM. My name's Leo. I'm a co-founder of AIM Group. And what we really do is we really try and understand the underlying physics of any asset. So it's about having complete understanding of what a structure or an asset is doing and how it can operate most efficiently. And we do this through a few different techniques that I'll go through. But that really is the powerful thing. It's about using all this pre-existing data to really have a firm, confident understanding and operating our asset in both the most efficient way and managing it in the most, with the greatest reduction of time, really, to make life quite easy. In terms of what our goal is, it really is taking thousands and thousands of assets and their vast quantities of sensor data and sort of validating the behavior, spotlighting exactly where to look, and keeping this asset running at peak confidence and efficiency. So we've been doing this for quite a while now, and we found some very good ways of doing this. In terms of who we've been working with, it's quite a large sort of portfolio of people now. So with Mott MacDonald, WSP, Network Rail, National Highways, Orsted, and instrumentation companies, as well as Innovate UK. So we're always trying to be on the forefront, working on some of the largest and most challenging projects and solving ultimately the most difficult problems. In terms of why we do this, why we say let's use data-driven AI, it really is because it brings a massive change to the industry. And so currently what we've been doing as engineers in terms of looking after structures and assets is there's been a lot of assumptive modeling, and we use a lot of that sort of engineering knowledge, whether it's through digital twins or inspections, and sort of applying that engineering knowledge with assumptions that this beam is perfectly uniform, that this energy transfer process is perfectly correct and perfectly, it doesn't have inefficiencies. And the difficulty with that is we're building in assumptions to our operations, and it makes it really challenging to have a real world picture of what's going on. And ultimately, it means that our assets get surprised. It really gives us a lot of sort of late interventions and a sort of poor understanding of how an asset can be optimally managed. What we've done is we've started taking data-driven approaches to managing an asset, really going from the ground truth of sensor data. And then we've been putting a machine learning on top of that to really understand what it's doing and predicting that behavior with about 99% accuracy. What that means is we can have a really good understanding of what an asset should be doing and really giving preventative insights such that we can understand, right, what is my asset doing? What should it be doing? What's the difference between that? And where are the problems? In terms of what we've sort of achieved in sort of the civil space as we bring this to energy, it's been reducing maintenance costs significantly by up to 65%, finding defects within structures far earlier by up to 3 years from what traditional monitoring achieves, as well as improving the operational confidence of an asset by about 10 to 50-fold. I will go into a little bit more detail about those statistics because they are just currently displayed on the screen with no proof. But this is really the sort of I would say the really powerful KPIs of what we've achieved in the civil space. In terms of what we've done just in sort of the last year and proven in the field, we've successfully helped support the reopening of the Hammersmith Bridge, taking an incredibly aging asset and going, yes, this is very heavily degraded, but actually this has further service life to give. So using machine learning, we've had a much greater understanding of what the asset is capable of and pushing it back into service. So what was going to be, hundreds of millions of spend on building a new structure has actually resulted in the current one staying in service. We've then taken this technology and deployed on the world's largest bridge monitoring system by data scale in the world, the Queensferry Crossing, with over 2,200 sensors, and sort of really proving that with machine learning, you can understand a structure at a massive scale and complexity. Where it was previously managed by a small team of people, there is now machine learning operating on this thing 24/7 and really having a good understanding of what the asset should be doing at all times. So it's really changed from going through, reams and reams of asset data and sensor data, thousands of these things, to just sort of a quick verification that machine learning is validating exactly what it needs to be doing, and also then just flagging engineering attention to the places that are required. We've then brought this technology to wind turbines, given that not only are these structures really critical, but they also need to be supplying energy and running for as long as possible. And so we've sort of proven, hang on a minute, there's a massive efficiency in this energy system. And we've delivered that with Innovate UK and the Offshore Renewable Energy Catapult. So that was the LDT research turbine up in Scotland, and really demonstrated this proof of concept that, yes, you can take the same machine learning, the same data-driven approach, take it from a bridge, and then put the same understanding to a wind turbine. We then worked with Ørsted to scale this, and now looking at trying to deploy this across fleets of turbines such that this has a real commercial viability and has the ability to, one, improve the efficiency of these wind turbines, but two, also be generating more energy in the same time, reducing that downtime. And that really means that, not only can we just sort of understand the asset better, but we can also bring the cost of energy down purely through machine learning on the data they're already collecting, which I find quite an exciting, fascinating thing. So in terms of how does this digital innovation work and what are we really doing? All of these assets have a large number of sensors trying to understand what it's doing and having a very sort of manual review process on them. Typically, this can be in the form of a strain sensor, a vibration sensor, or maybe it's an electrical output. But really, it's something you can plot on the screen, something you can go and look at and go, right, is this behaving as I expect? Is this what normal behavior looks like? And the challenge here is that we only have one reading and we have nothing to compare to. And so it's a real challenge to know if something's behaving correctly or not until you see a massive outlier. And by that point, it's too late. We've already got problems and we've got quite large concerns that we can't preempt, and we can't have that kind of preventative maintenance, forward-looking approach. And there's a lot of efficiency we're missing out on. What we do instead is we're taking that data, we're running it through machine learning in such a way that you learn the underlying physics of what's going on. And I must state, there's no modeling, there's no assumptions. It purely is setting up and learning the physics of the asset such that we can understand if tomorrow's weather looks like this, or if the weather at that time looks like this is what the asset should have been doing. And we learn that to a remarkable accuracy. And you can sort of see in those two graphs there, the sort of level of accuracy we're bringing, considering this machine learning has never seen this data before. So when we have that real fundamental understanding of what the data is doing and what the asset should be doing, we can then have both a very good approach in terms of preventative maintenance and going, hang on, this asset is not behaving as we expect, and finding a problem early. But also we can validate an asset that it's capable of operating even when there previously was concern, because it's still doing what normal behavior looks. And this is exactly what we've done to sort of the Hammersmith bridges of the world, where we look at really aging, struggling assets and going, actually, we can push this for further service life because it's doing exactly as we expect and it's not degrading any further. It can be moving lots, it can be in a very challenging set of operating conditions, but actually it's still fit for service. And this is the sort of architecture we apply across structures and energy assets as well. In terms of where we sit, there is all sorts of infrastructure. There is the sensor data reporting how it is performing. And it really is just a data processing layer on top of learning the underlying physics and going, actually, this is exactly what we expect it to be doing, or otherwise flagging where it is concerning And the exciting thing here is as you scale with the data and you move on to more and more complex assets, especially in the energy space, it really becomes a validation process of validating every sensor automatically and just flagging the 3 or 4 that are concerning. And that's really the exciting thing here is now you've got a very automated way of understanding an asset with all the data still at your fingertips. And that really is just from understanding the pure physics of what's going on. I talk about physics quite a lot. In terms of accuracy, the sort of typical accuracy we're looking at is above 99%. The metric we used for that is R squared, which is if you achieve an R squared of 1, it means you have a perfect understanding of the asset. And so when you're hitting about 99% through all ranges of conditions and things you haven't seen before, it's really because we're learning the physics and not trying to model or understand something with assumptions. It is purely a data-driven process. So on one, we have a sort of a raised highway just showing this. And then the other, we also show a marine asset. And this was quite an interesting one because sensors were only installed as this asset was degrading. So we have this massive problem of can we understand and train on something that is actually a really sort of challenging frontier problem because it's degrading at the same time. And you can see by about day 2, we hit about 80% accuracy. And by about day 9, we hit about 90%. So it really shows that it's all about sort of setting up the problem, understanding the physics, and you can have a really good fundamental understanding of how this system should be behaving. And so whether it's bridges or turbines, it really is just about knowing the underlying physics of the problem, of the asset, and then going, is that behaving consistently? That's really the powerful thing in terms of building scalable data that's really going to be useful for an asset to actually have an operational efficiency gain. In terms of how we do this as well, one of the biggest things that's been key to us is actually making sure that this can be launched very rapidly. It's one thing to be developing all this and having a very good physics understanding. But what I like to show here is that this can actually be deployed incredibly quickly. And it's just about making use of the existing data. We've done the hard part, we've installed the sensors, but actually we can get most of it if we have something to compare to, if we have a baseline, if we have a fundamental understanding of what the asset's doing. And it's really as simple as 1, 2, 3, selecting the sensors, making sure it's high quality data, and then really running the AI such that we can have that breakdown understanding, and then we can really find out if the asset's behaving and how we expect it to be doing so. In terms of the opportunity, and this is really the exciting part, is we're now in the 21st century where we put sensors on everything, and it's absolutely brilliant because it means wherever there is sensors, it really can be deployed. So whether it's infrastructure, buildings and construction, energy, or plant, it really is about taking that sensor data, understanding the fundamentals of that process, and saying, is that consistent? Is that continuing? And then therefore, what are the efficiencies we can realize from it? So it's the same machine learning architecture applied 101 different ways to the real world to really manage these assets. That's the exciting thing here. The thing we've really tried to do is make sure that this is low risk and high reward. So in terms of, it's been a lot of R&D, about 5 years or so, but what we've managed to achieve is by requiring no new hardware and using just the sort of sensor data, working with any sort of sensor provider, and being able to do this across a fleet of assets and making it safety critical, it means that we can deploy almost anywhere with a very meaningful impact. And the thing we always like to say is manage thousands of sensors across an asset in a cup of coffee. Brilliant. Thank you very much. I hope that wasn't too long of an introduction to our sort of technology, but I'd be happy to take any questions.
Hello. Right, there I am. Thank you very much for that overview. I've got quite a few questions. Hopefully you don't mind answering. But also in the chat, please add any questions from the audience you might have about AIM or to Leo. I've got a few things here. I think it's quite interesting. It's very interesting this, and taking this data and obviously is predicting faults and anomalies and things like that. What's just a sort of a clarification point in terms of response times, like sort of how quickly do the models sort of identify anomalies, and how quickly sort of that sort of gets identified and then you can respond? Can you tell a bit more about that and where you're applying that?
Absolutely. So there's 2 things to consider when you think of what is the response time. The first one I'll say is, which is just finding out as a person operating day to day. And that is, it has to be real time. That's where you're going to get the most response. And, if we want to be chasing these finding defects 3 years ahead of where they typically are. It has to be real time, taking live data and then going, right, this is the deviation. You've caught it from as soon as it's deviated. The second I'll talk about is also the machine learning's confidence in what it's doing. And so it will be looking for what is the acceptable behavior that is quote unquote normal, and when does that deviate from the normal so we can find the problem. And so if you have a very, very wide range of what machine learning thinks is good, it means you're going to find a problem very late. So even though it's in real time, you're going to find a late problem. What we do is we train it very aggressively, like I said, on the physics to really bring that confidence down and to really be finding problems as soon as possible. So there's two things I'll say. It has to be real time, and it needs to be years in advance of where you traditionally find the problem, such that you can prepare for it. In terms of context for a wind turbine, if you found out the gearbox is going to fail a day before it actually does, it still means you're going to be waiting on shipping and components, and the turbine's not going to be generating electricity in that time. If you can know it's on a collision course for failure 3 years in advance, it's a dramatically different outcome where you can really plan this in and you'd have minimal downtime.
Brilliant, thank you. Robbie's got a question, but I think I have one that leads into this, so I'll ask mine first. One question might be, how much is there a point where you think the improvements sort of saturate, where you feel like actually we don't need any more data? I mean, it's a very sort of general question, but maybe you can frame it within your own applications. But have you found that obviously there'll be diminishing returns, but do you find that actually is the sensor data that's already on these assets pretty good for everything you need to do, or do you often find that actually you do need to add, some sensors on this? Because I guess this plays then into the cost of things, right? Because monitoring can be expensive.
Understood. Well, I think ultimately the first thing I'll say is any kind of return has to be economic for this to make sense, and that's really the critical thing here, is to use technology to make things more efficient, and that's really what we're excited for. And I think that's what everyone wants to see. Cost of living, etc. We don't want to see another add-on in that regard. So putting extra sensors on follows the same sort of approach, which is we're going to be costing a lot of money, and we have to look at the returns for that. I would say in everything we've deployed on up to date, we have not needed to add extra sensors, and it really is about understanding the fundamentals. The reason I say that as well is because ultimately, before machine learning, humans were assessing this data. So humans had to have enough data to really understand the problem and what's going on. Whether they catch it, late or just about on time, they still need that sensing in place. So machine learning is really just being able to have more capability than a human with the same volume of data. So typically the problems we look for that the sensors were installed were already there. We're just finding the efficiency. I'm sure this will bite me in the future when I work on an incredibly complex problem. But for the time being, at least that's the answer I can give. And that's what I'm confident in our work today. But I'm always ready to be humbled.
It's on record now. I mean, you mentioned physics and obviously machine learning. So physics feels to me it's very like, old school kind of stuff. And then you're talking about machining. Can you maybe talk about that balance? How much of this is physics and how much of this is sort of the data-driven methods? Because there's sort of two cultures almost, really, aren't they?
Understood. The first thing I'll say is there's a massive responsibility when using AI and machine learning. Despite being a massive advocate for AI and machine learning, I personally believe that 90% of it is not of use and is currently more of a exciting prospect that can't be independent and has to be supervised. And you sort of add a layer of complexity that sometimes gives efficiency, sometimes gives the illusion of efficiency. You see this a lot with generative AI, where it will be saying whatever it needs to get the task done, but it might not be correct. A case in point is myself asking Claude to make these slides today and then spending the following 3-4 hours making the actual edits itself as a prime one. In terms of what we do, the truth is, I'm an advocate of machine learning for its vast ability to do data scale, and it really brings a massive component of, right, we can do this automatically on its own, on a far more sophisticated way than just a simple algorithm. But the really important thing here is to have your fundamentals correct. AI is a tool in the toolbox, and we cannot neglect all the other tools. So when we say physics, it really is about using our machine learning team to set up the problem correctly, such that machine learning can be trusted to independently run it. And then we just need to check in on validations. That's really the exciting part here.
Absolutely. Yeah, I have a question about foundation in a minute, but I need to get to Robbie's section first. But I
By
guess
all means, I'm
I, I'll not hug the questions, but there's a few now in the chat, so I'll get to those. So we talked a bit about lots of data, but Robbie's asking here about sort of the opposite here, really, which is actually how do you deal with the fact that actually there's very little failure mode data actually collected and available for AI training? Should we be testing assets to destruction occasionally, perhaps at the ends of their service limits?
Well, first of all, Robbie, thank you very much. That's a really good question. So this was one of the very intelligent things we had to design about the architecture, is it's about learning normal and deviating from normal. And that's really the intelligent thing we've had to do in terms of how we design this thing, which is that if you're learning what normal behavior is and you deviate from it, then you're approaching your failure mode. And that's really where it gets flagged to an engineer. The one thing we never do is we never let an AI just flag it and then make the decision and sort of cut the human out of the loop. It really is about being that early warning system of approaching failure mode. So we've done this on all sorts of challenging applications. The really important thing is if you're predicting normal, you need to be able to capture every single failure mode. Otherwise, this is not going to be a useful general solution. So what an example I'll give that's very useful is we've deployed this on a cast iron bridge. And if you know anything about cast iron, it's incredibly brittle. It's like glass. And so even in something which is incredibly brittle, it still has a very, very slight deviation before it just shatters. And so it's about having such a high tightness and confidence of what normal is that you can find that deviation before. And that's why we always try to aim years in ahead of a failure, because then we can really not only see this failure early, but track it and then let the engineers do the analysis to really understand what is the failure mode.
Brilliant. Thank you very much. Terry has a question. So how does the asset monitoring interoperate with the existing standard management of the assets? So a very good pertinent question on interoperability, which is always important here at the Catapult.
So I will humbly say, in all of the most difficult challenges we've faced in machine learning, physics, and all of these challenging subjects, the hardest thing has always been integrating with the asset management plan. Every company has a different plan, has a different way of doing things, and the truth is, the first thing to do is not disrupt their plan at all. Just have it run in the background, and then let them get comfortable with it. If they see what their asset is going to do a day in the future, when we've seen what the weather is, what the environment is, etc., it can really predict it, and then the asset manager starts to trust what we're doing because we're talking the talk, and then our machine learning has to walk the walk. Once we're doing that, they can then start to utilize this machine learning and trust it and go, right, this is how we're going to use it. A good example is the Cleveland Bridge in Bath. And this is an asset we've had for 5 years that had a 3-ton weight restriction. It was just saying no heavy trucks on it allowed at all. And we can't come to these guys and go, hey, actually, just put massive trucks on your bridge. It'll be fine. The machine learning says so. What we do is we just let it run in the background, and gradually they put heavier and heavier loads on until they started to trust the asset. But that very much is a case of culture and change. And it's one of the things we're really excited to be doing with Orsted, is because they want to be looking at this and going, right, the innovation team's going, okay, what can this mean in terms of asset management, and what can this capability bring? And truthfully, it's the same disruption from going from having an inspector to going and having a sensor do the measurement. There was a period where that was a really taboo topic, right? And so we've just got to continue to work with them to really get this technology out there.
Just going back on then that point about sort of those extreme events, I guess. Is there you say you try and map all of them, but obviously there's the famous unknown unknowns. Do you counter those many in this area? I mean, I guess they're the sort of events which are one in a 100,000, one in a million type events, and I guess even with a physics-based model, there might be a limit in what's maybe even modeled in that area, I guess.
Absolutely. Well, I think it would be very silly for myself to say no. We don't have unknown unknowns. I think possibly one of the worst things you can do. No, everything has unknown unknowns, and that's one of the very exciting things that we've had to do in this model, and probably one of the most challenging things we've worked on, is actually how this technology works. Is we're bucketing our data we're collecting, because it's not the full picture. It's only where the sensors are. And so we bucket it into known knowns, known unknowns, and unknown unknowns. And that's why when you see in some of these slides, the AI actually reports its own confidence. you see a dark green band, and then you'll also see a light green band as to what is acceptable. And so that band can change in width and size depending on the different factors and the measurements we have against them. That's the exciting thing here. So there are so many unknown unknowns. The question is, can you make those about 2% of the picture? And then you can really have a very high confidence understanding of what that sort of range of acceptable behaviors is. And then when those unknown unknowns do happen in terms of a concerning event or, a heat wave or whatever it is, one, the AI will raise its confidence massively. You'll see that and you'll get an alert of it. And two is you'll see a deviation from normal that gets flagged and gets raised to engineers for attention far before anything catastrophic happens. So again, it's really in the architecture of how you set out machine learning. It really is just a responsible tool.
Great, thank you. While you're on there, actually, you show the sort of uncertainty bands. Like, how key is that? Is that changed much? Do you feel like, obviously, the stuff you're dealing with now have a lot more uncertainty levels, and that's been a key, the sort of probabilistic component is now increasingly important, or, is it always been there, I guess?
Oh, okay. I would say in any engineering problem, there is always a probabilistic unknown element because we make such big assumptions. And so that's why, if you're ever in a lift, it will give you a weight limit, and then they'll actually load it to 50% more than what you expect. With machine learning, it really is bringing that tightness down because we've got a much higher level of accuracy through sheer computation and understanding. So those unknown unknowns are always there, and those challenges and assumptions are always there. It's just about making those as tight as possible and having as high accuracy.
And those things are obviously dependent on more data usually, right? So because obviously you're modeling a distribution rather than an individual estimate in these cases.
So I'm going to both agree and disagree with you,
Okay.
which is that
That's the best
I am
type of
all
answer.
for more data, but there is a massive issue in our industry, which is we build machine learning models and then we input data and then we look at the results and go, hang on, that's not quite accurate enough. There must be something wrong with my data. And so we're very quick to criticize data volume and go, if you just scale data, it will do better. And sometimes you do see this with companies like Anthropic and OpenAI, where they're really just desperately scaling with data. But the truth is, model quality is a massive part of this. And so, yes, we do always look for more data. Yes, we do like it. But the Queensbury Crossing had 2,200 sensors, and that's phenomenal for us. But we've had to go to bridges where we've had just a crack and a single sensor. And so it really is about improving model quality. And I would say constraining yourself with data is actually one of the best things you can do to get high quality models. A good example of this is how China are developing, generative AI models with way less compute, way less data than the US are, but they're trying to go with parity. And that's because they're focusing on really high quality models. So it's not to be neglected.
Yeah, absolutely. Brilliant. Thank you. I'll get back to the questions on this rather than selfishly taking the questions space. Just one quickly, Diraj. I guess if you maybe if there's a specific thing you're asking there, I'll probably ask you. It's probably quite a wide question. So if you've got anything specific on that, then I'm happy to ask it. But maybe you need something more. I need to know precisely what you mean there. Terry has another question actually on. Have you had any projects in the telco sector? Cell sites could be a good candidate. It does feel like it's sort of there's a lot of overlaps perhaps in that. Do you consider what sort of areas are you looking in more widely?
Sorry, what sector was that? Sorry.
Sorry, telecommunications. Sorry.
Telecommunications, yes. It was actually one of the things I was working on pitching 2 days ago. It's a very exciting space because it needs critical levels of uptime, especially in sort of the 5G tower space. So we're actually speaking with the DBT in Australia about this, given their sort of high density of cities and really high need for uptime. But yes, telecommunications is a massive area of this, and we really want to get involved. One of our biggest challenges is there's a million and one problems to solve, and only one startup currently with this sort of architecture. So we do pick and choose our battles, but telecommunications is a very exciting area.
Do you find is there is there any sort of thoughts, rules on how easy it is to adapt something to a new sector? Is sort of what's the when you're sort of not to put you on the spot, but when you're moving to a new sector and there's the idea to take something you've done in transport to sort of the energy sector. Is it, the
Mm.
core models are sort of similar, or is it really, the fundamental thing is the domain knowledge and the physics kind of, as you mentioned?
Okay, so there's two answers I'm going to give, and one is from my perspective as the sort of person running strategy, which is this is easy, this is
Oh,
great. We just need to understand the problem and set up the physics correctly, and then the same sort of machine learning approach can be rapidly implemented. From my CTO's perspective, I'm sure he's very angry as what I've said just now.
no.
It is a massive challenge and a massive responsibility to set up the problem correctly. Just as you would as an engineer, right? If you're using the wrong equations or the wrong assumptions, you're going to get the wrong answer.
Yeah.
So it's easy if you do it correctly, and it's very challenging to get there. As we've spent about 6 years in this industry doing the R&D and going, what are the fundamentals? What is the architectural approach to get this correct? It becomes easier and easier, and so we look at quite rapid improvements.
Yeah. It wasn't a trick question. I guess my sub point was like,
Mm.
what sort of ingredients are key, I guess, to doing this, because obviously the you know you've got all the learning from working in these sectors, so that it does put you in a good place for doing that.
Mm.
What's the sort of is there's key components that when you do think about moving to another sector, that these are things that are fundamental to what you do, really.
I think the most fundamental thing is every sensor is a lens to the problem, which you can view it from. And you need to make sure that either data they have or data you're going to collect from outside externally through APIs and all sorts is enough to have a rough understanding of the problem such that you can have high confidence. Um,
Mm.
you've also got to pair
Yeah.
that then with the economic impact you can have and the efficiency you can realize. Some systems are so tightly run they don't need machine learning. And so you've got to balance those two things and go, right, what is the opportunity here? And does the data enable us to get this level of insight?
Thank you very much. Okay, there's a question here from Edward. How robust is the system to changes in operating regimes? So, for example, if an asset normally operates differently across seasons, maintenance states, loading conditions, or changing control strategies, how does the model distinguish legitimate behavioral change from, say, degradation? So
That's a
dealing with
brilliant
that
question.
non-stationary elements, I guess.
So there's two challenges we've had to solve. One is training on an asset that is continually degrading. No asset is perfect; it always gets worse. Yet you're trying to constantly update your model. So that's a really challenging thing, and the machine learning has to know the confidence of each bit of data it's training on. Um, the second, in terms of having a really good in terms of having a good understanding of how to, I would say, train and look at every sort of mode of operation. So I'm trying to think of how to answer this in a very useful way.
I guess it's sort of these conditions where, certain of these, like certainly in energy, there's varies in temperature, right? I guess. And then you're learning one regime will be like summer, one would be in winter. I guess is it sort of one big model that takes into account all of these things?
yes.
Or is
So
it sort of, is it adapting as you go along and therefore means you sort of have to do two things at the same time?
so there's two sides to this, and it's I'm just trying to think of how I explain this in quite a
Yeah.
a rapid way, if I may. But the first thing we do is we stress test our models. So one of the core things we do is we will take purely summer data and then predict an asset's behavior in winter is one example. And as such, you've got a massive extrapolation there of a different sort of range of characteristic operations. And the first thing you want to see is this actually useful? Can we give a high confidence answer of what is expected and achieve that sort of R squared of above 99%? That's the really important thing. And yes, we do that. And we're very responsible around that and have tremendous liability. So we have to be good at that. The second thing I will say is for very unexpected things, let's say if you're looking at wind and then you get hit by a hurricane or something, right? Something, really in the extremes. The machine learning will take that sort of future behavior coming in, the whatever wind expectation it is going to be, and its confidence will change dramatically. So again, the architecture of the machine learning is to say, hang on a minute, watch out. This is something that's really concerning. that we've never seen before and is going to be such a major extrapolation. And so the machine learning needs to know its own limitations. It's very, very rare for this to happen. I don't think we've ever actually had this happen in real life. Typically, there's not been many hurricane style events. But then it alerts that, it shows that. And then most importantly, after the event, we also look at, has it returned back to normal or has its characteristic behavior changed?
Great. Yeah, I was actually going to ask a bit about that. You said that, hurricanes, but obviously there's we've had a very hot summer and some,
Mhm.
I guess you call unusual events. With your physics modeling now, are you starting to look a bit more externally in sort of what is happening, with weather, climate, maybe even markets and things which might affect the asset? Is that part of the model as well, or is it primarily on the sensor? What's your thoughts about incorporating that information?
So all of that stuff is incorporated, is the first thing
Yep.
I'll say. So
Okay.
we take sensor data that's already there, and then we API in everything externally because there's such a large open source community of data. It's really to make the life easy for the client that we say, send the data
Mm.
that you have on your sensors and send your location. With the location, we pull everything else in. So whether that's a wind turbine, a bridge, we're pulling in the temperature at that location, etc., and really building that in as part of the sort of environmental factors as an input and going, how is this going to affect the response? And then in terms of, let's say you have a heat wave, that behavior will be slightly different to what was yesterday. And you'll see that in probably greater expansion, etc. We're sort of factoring that into the sort of physics-based understanding of the problem. And then if the structure physically changes and it has some sort of degradation, you will see that because it deviates from the already updated prediction. And you'll see that actual removal. So it's quite a challenging thing because when you've got behavior, you've got to quantify what is healthy and what is unhealthy. And that's why we have a baseline.
Are you anticipating things coming down the line, maybe, or is that something to start thinking about? With obviously heat waves and
The
possibly
truth is that
El
as
Nino
a
next
person,
year.
as a person, I cannot anticipate these things. They would
Mm.
definitely be coming in higher volumes. But it is really up to the machine learning to flag it because it can find it far earlier than I ever could.
Okay, thank you very much. I'll just there's a comment from Robbie which I think is quite interesting. He's talking about the A100 Ringbahn Bridge, a couple of kilometers from Berlin, and that recently developed cracks and will be out for years. So it kind of just highlights a good example of how
Mm.
important some of this can be. Um, and just maybe one last question then as well, unless anyone else has anything to add on here. We've interrogated you a lot already.
No,
Um,
you're more than welcome to. I love challenging questions.
This has been very useful. Yeah, so Terence asked a question about using AI ML to handle situations where not all assets have sensors for monitoring to draw wider conclusions. And I think it does go into some recent trends in foundational models and generative AI, as you mentioned. So transfer learning, I guess, was the old
Mm.
word for it. Have you looked at that, I guess, like where you have zero shot modeling, where there's no information and you just don't like what level of capabilities can you take from training all this stuff you've got? Or what do you see as maybe the potential there, I guess?
Um, I will say we have looked at this. There is potential, but ultimately, the thing we're after right now is really concrete reliability for asset owners. And that's really the thing that's going to really make them a useful management outcome. The challenging thing there is every single asset is unique. And even if you have a series of the same turbine, bridge, power station, as soon as it develops a crack, it is a different thing with a different set of behaviors and its whole normal operating regime is different. So you have to be incredibly careful. And it's been very rare to see this kind of approach work successfully. As far as I know, we're the only company that can do this. To remove these sensors, I would not be confident in as of yet.
I guess it's also they'll probably change as you get more data on so it's almost fine tuning, right, as well. That might be an aspect. But how much data that's maybe a different question, but I guess
Go for it.
is there, and it's a very, very general question, so maybe not that easy to answer, but do you have thoughts on, how much data you really need in terms of history and things to really learn an asset? Is there, I guess it
It
might
depends.
vary.
It depends on the external factors that affect its cyclic behavior. So typically for a structure that's very thermally driven, you typically need about 6 months data. And we typically find with most structures, that's what we're looking at, is because you're going through the sort of summer, winter temperature regime, and you can see that difference. And if you can, if you can train on summer and predict winter, then if you train on everything, you've got a far stronger model that's incredibly robust to all these sort of outlier events, etc. Whilst having that high confidence. In terms of what we try and do is try and train on as little duration as possible, and then give the ML the full set of data. So we will never turn down more data, but we don't want to be dependent and beholden to it.
Right. Yeah. Got it. Well, this has been brilliant, actually. So thank you very much. I think we're at the end of our questions, unless anyone's got anything they just want to push in. But this has been a really, really interesting. I've enjoyed chatting with you and learning more about this. I guess you put your contacts on the slide there, so you're happy for people to contact you if they have further questions. Brilliant. We recorded this, so we'll put the chat on the YouTube, and everyone who's registered will get the link to that anyway. And I understand you'll share some slides, Leo, of that we can send around as well, so to those registered. So yeah, all I have to say is massive thank you very much. That's been very interesting. It's great to hear about sort of these things in the field. And so yeah, thanks to the audience as well for all the questions. And yes, I saw a hand up. Is that was an accidental clap that we're turned into?
I think that might have been an accidental one. But well, yeah. First of all, thank you very much for all the questions. Really good. Sometimes challenging, but no, I love that kind of thing. So absolutely brilliant levels. Thank you.
Enjoyed it. Brilliant. Well, thank you, and see you all next time. Take care.
Brilliant. Until then, cheers.